Hi guys, in this video I will try to describe the concept of clipping algorithm in computer graphics. So what is clipping first of all, and why it is used? The primary use of clipping in computer graphics is to remove objects, lines or line segments that are outside the viewing pane. So to understand why we actually need clipping, just let me go back to the previous tutorial, which was about window to viewport transformation for a moment. Just look into this diagram. You have an entire set of objects defined, and this was your clipping window. When you transform the contents whichever are visible through the window, first you need to clip or truncate the portions outside the viewing window. So some sort of clipping is necessary here, and the goal behind clipping algorithms is to achieve this. Now let me go back to our present lesson. Basically, in computer graphics, your screen acts as a 2D coordinate system. How? Uh, Say this is your x-axis, sorry, I have to enlarge the font a little so it gets visible, and this is your y-axis. And now define your viewing pane, which is essentially a rectangular window. If you can recall our previous videos, then this rectangular viewing pane can be defined with four coordinates for its four corners. For example, once again, the coordinate for the upper left corner is x min, y max. The coordinate for the upper right corner is x max, y max. The coordinate for the lower right corner is x max, y min, and lastly the coordinate for the lower left corner is x min, y min. So this was the definition of your viewing window. You have mathematically defined it in terms of four coordinates, right? Next, what is the idea behind clipping. Actually, what happens, you can only view the points which lie in the particular range of this viewing window. Say you have a point x1, y1 here, and you have a point x2, y2 here. So just try to figure out among these 2 points, the point x1, y1 and point x2, y2, which will be visible to your viewing window if the entire coordinate system is your world. Just give it a thought and let we come back to our clipping algorithms. So the simplest type of clipping is point clipping. In point clipping, what happens? You only be able to see or print the points on your window which are in range of your viewing pane. Other points which are outside the range are discarded. For example, just look at the viewing window in the example of the tutorial. The green region is your viewing window. You have 4 points here in your world. Entire gray region is your world. You have 5 points here: point A, point B, point C, point D and point F. So if you are looking at your outside world through this green viewing window, you can from observation say that only the points A, B and C will be visible. D and F are outside the purview of the viewing window. So these 2 points will be clipped when you translate the entire thing into your viewport. And the diagram below, this diagram actually depicts the scenario after clipping. Here you can see that only point A, B and C are retained. Point D, F are discarded or clipped. All the points outside the viewing pane are discarded. So what is the point clipping algorithm? How you can translate this concept of point clipping in terms of algorithm? It goes like: get the minimum and maximum values of x and y coordinates of viewing window. Then go to the next step, get the coordinates for a point. Third point is check whether given input, in this case the points lies between minimum and maximum coordinate of viewing pane. Lastly, if yes, that means if the condition of the third point is satisfied, it implies that the point is lying inside the region. Otherwise, what you have to do? You have to discard it. So now try to establish this point clipping algorithm in mathematical terms. For that, let me go back to our diagram. Here you see what is the minimum x value of the x coordinate points. It is x min. So minimum x coordinate value equals to x min. Similarly, try to figure out the maximum x coordinate value. It is x max. In similar way, try to figure out the minimum and maximum y coordinate values. Minimum y coordinate value in the red window is y min, and maximum y coordinate value in this system is y max. So just apply some sense of observation. Actually, the point to be visible, its x coordinate value must lie within the x coordinate range of your viewing window. In this case, the x coordinate range spans from x min to x max. Similarly, for the point to be visible, its y value must lie within the y range of your viewing window. Explicitly, the y value must lie within y min and y max. Now let's try to explain this in mathematical terms. For a point x, y to, let me drag this thing here. For a point xy to be visible, following conditions must hold. And what are the conditions? The x must lie within the range of x min to x max. It implies x min must be less than equals to x, must be less than equals to x max. Similarly, y value must lie within the range of y min to y max. So y min less than equals to y less than equals to y max. Just repeat it once again. For a point xy to be visible, following conditions must hold. X min must be less than equals to x, less than equals to x max, and y min must be less than equals to y, must be less than equals to y max. So now apply the algorithm to our diagram. Here you have two example points. One is x1, y1, another one is x2, y2. Just apply the algorithm for these 2 points. If you look at the insight point, that is x1, y1, which from observation you can establish that it is inside your viewing window. Actually, what happens? These 2 conditions hold. How? For the first point, that is x1, y1, x min less than equals to x1 less than equals to x max, and for y1, sorry, a little mistake, for y1, y min less than equals to y1 less than equals to y max. So for the inside condition, you can say that this condition holds. Now, if you look at the second point, the outside point, which is x2, y2, you can see that this condition will actually not hold. Just give it a thought. If we put x2 and y2 into this algorithm, will this conditions hold? No. The answer is simply no. Why? For x2, you can see that it is obviously greater than x min. x2 is greater than x min, but it is not less than x max. It is greater than x max. So this condition does not hold. For y2 similarly, yes, for y2 this condition, sorry, I was wrong. For x2 this condition actually holds, but this condition do not hold. So from this discussion, you see we have got one justification for this establishment. So this was the mathematical definition of your point clipping algorithm. Now let again we go back to the course material. Situation is not always going to be such simple that you always have to clip points. In the course of time, complex geometrical diagrams will come onto your way, which you have to clip. Actually, as per our syllabus, you have to study point clipping, line clipping, and polygon clipping algorithms. So, for line clipping algorithm, you have to study 2 algorithms: Cohen Sutherland line clipping algorithm and Cyrus-Beck line clipping algorithm. In this video, we will only study Cohen Sutherland line clipping algorithm. So, for the time being, just have a look at what is the concept behind the line clipping algorithm. The concept of line clipping is same as point clipping. In line clipping, we will cut the portion of line which is outside of the window and keep only the portion that is inside the window. Uh, just again come back to this diagram and no, let me define a new viewing window. Sorry, uh, this is our x-axis, this is our y-axis, and the green box is our viewing window, which is again defined in terms of x max, x min, y max, x max, y max, x min, y max, and you yourself just pronounce the coordinate for this lower left corner. Now, what is the general idea behind your line clipping algorithm? Say this is a line which you are looking at through your green viewing window. You just have to keep the portion of the line which is visible through the clipping window. This is the visible portion of the line, and whatever is there outside the viewing window, just clip it or discard it. So sorry, here in Cohen Sutherland line clipping algorithm, various situations might arise. First, have a look at the general statement for Cohen Sutherland line clipping algorithm. The Cohen Sutherland line clipping algorithm quickly detects and dispenses with two common and trivial cases. To clip a line, we need to consider only its endpoints. This is an important line. To clip a line, you need to consider only its endpoints. Later on, we will try to figure out why. Now come back to the statement. If both endpoints of a line are inside the window, the entire line lies inside the window. Just give it a thought. If both the endpoints of a line lie inside the window, here look at the line AB. The endpoints of the line AB are A and B. If you have a look at the visibility of the endpoints of the line AB through your window, you can see that both the endpoints are inside the viewing window. In that case, Naturally, you have nothing to clip. Do you need a clipping? No. Do you need to discard any portion of the line? The answer is no. So, you can conclude that this line or this categories of lines will be trivially accepted and needs no clipping. Now, on the other hand, if both the endpoints of the line lie entirely to one side of the window, the line must be entirely outside of the window. It is a little bit complicated. It is trivially rejected and needs to be neither clipped nor displayed. What? Think of it once again. On the other hand, if both endpoints of a line lie entirely to one side of the window, not outside, then the line must lie entirely outside of the window. Just have a look at the line CD. Now, the endpoints of the line, the point C and point D, actually lies entirely to one side of the window. In this case, what will happen? This line will be trivially rejected. Actually, this line will entirely be not visible through your window. You can trivially reject it. So, one third case which might arise is, say, you have a line like this. Say the endpoints of the lines are E and F. Now, have a careful look at the nature of the endpoints of this line EF. If you look at the point F, it is lying inside your viewing window. And if you look at the point E, it is outside the viewing window. So, how it goes on? The point F is inside and point E is outside. So, this is actually a third type of case where you cannot apply those trivial acceptance or trivial rejection conditions. Why? Because some portion of the line will be visible through your viewing window. Here, the portion of the line which I have highlighted with red second bracket will be visible. But if you look at this portion of the line highlighted with green second bracket, it will not be visible. So here you need to clip this portion. So now we have three types of situations which might occur here. First one, trivially accepted when both the endpoints of the line lie inside your viewing window. Trivially rejected when both the endpoints of the line are at one side of the clipping window. And a third situation where the line is partially visible. Now you need to derive some mathematical or algorithmic solutions by which you can find which case will be applicable to the line in concern. And this is the idea behind Cohen Sutherland line clipping algorithm. Let me move on. Uh, Let me go back to the next page of the lecture. Yes, here it is. What does it say? You have to establish some inside-outside window codes by following Cohen Sutherland line clipping algorithm, as the idea is to determine whether the endpoints are inside or outside a window. The algorithm actually sets up a half space code for each endpoint. Each edge of the window defines an infinite line that divides the whole space into two half spaces, the inside half space and outside half space, as shown below. Let's look into this diagram. Okay, if you look at the dotted clipping window and extend this line up to infinite, then you can see that right side of that infinite line, which is shaded in gray in this example, will be the outside portion to the clipping window, and left side, this side, is going to be your inside portion with respect to this edge of the clipping window, and this is termed as half space. You need to assign some code mechanism to your endpoints with respect to this half spaces, outside space and inside space. As you proceed around the window, extending each edge and defining an inside half space and outside half space, 9 regions are created. The 8 outside regions and 1 inside region. Let me try to derive this in our example. Just erase everything and draw the world and your viewing window once again. And what it has told into the statement, it has been told that you have to extend each and every edge to infinite. Say we have extended the upper edge to infinite, plus infinity, minus infinity. Similarly, you have to follow the same thing for remaining 3 edges. Left edge done with right edge, done with bottom edge. So these all are actually extended to infinity. Just write it down for your reference. So just now observe the entire diagram as a whole carefully. What we have achieved by extending the edges up to infinity. Actually, if you notice, by doing so, we have divided our entire space into 9 regions. How? Region 1, region 2, region 3, region 4, region 5, region 6, region 7, region 8, and region 9. Now, again, these 9 regions can be partitioned into 2 categories. Region 1 is basically an inside region. Inside region. Region 1 is inside your clipping window, and the remaining 8 regions are actually outside your clipping window. Outside region, 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 and the last outside region. So this is what has been said in this portion of the note. You have created half spaces with respect to each and every edge, and as you proceed around the window extending each edge and defined an inside half space and outside half space for each and every edge, 9 regions have been created, the 8 outside and 1 inside region. Now, each of the 9 regions associated with the window is assigned a 4-bit code to identify the region. This is again an important line. Each of the 9 regions associated with the window is assigned a 4-bit code to identify the region. Each bit in the code is set to either a 1 true or 0 false. If the region is to the left of the window, the first bit of the code is set to 1. If the region is to the top of the window, the second bit of the code is set to 1. If to the right, the third bit is set. If to the bottom, the fourth is set. The 4-bit code then is used to identify each of the 9 regions as shown in this diagram. By doing this, you are actually generating a code sequence which you can term as LRBT code sequence: left, right, bottom and top. And the conditions are something like this. First bit is set to 1 if the point lies to the left of the window. Second bit is set to 1 if the point to the right of the window, x greater than x max. Third bit is set to 1 if the point lies below the window, y less than y min. Fourth bit is set to 1 if point lies above the window, y greater than y max. So this is the thing which at first you need to establish. So what you have to do? You have to generate LRBT codes for your endpoints of the line. Let me try to achieve this with an example. First, draw your viewing window once again. And define x min and x max, y min and y max for all the four corners of the clipping window, as you have done before. Sorry, x max, y max, then again lower right corner, it goes like x max, y min, and lastly the bottom left corner, it is x min and y min. And for our reference, what we can do, we can just copy this line and keep it nearby. Yes. Now, say, sorry, this is our line in question and the endpoints are defined as P1 and P2. Now, try to generate LRBT codes for your P1 and for your P2. The algorithm was like first bit, that means L bit, will be set to 1 if the point lies to the left of the window, that means x less than x min. Say this is x1, y1, the coordinate for point P1 is x1, y1. Now, the algorithm says that assign 1 to L bit. This is going to be a 4-digit binary number. Assign 1 to the L bit if the x coordinate of the point in concern lies to the left of x min, that is x1 less than x min. But if you look into this diagram, in this case the condition doesn't hold. x1 is indeed greater than x min. So the L code will be set to 0. Now come to the R bit. Second bit, that is the R bit, will be set to 1 if the point lies to the right of the window, that is x becomes greater than x max. R bit will be set to 1 if x1 lies to the right half space with respect to x max. But in our present example, it doesn't happen. x1 is to the left of x max. x1 is on the left half space with respect to x max. So what you have to do, you have to set r bit again to 0. Now come to the third bit, that is b bit or bottom bit. Go back to the condition. Third bit will be set to 1 if the point lies below or bottom of the window. That is, y becomes less than y min. The third bit, b bit, will be set to 1 if your point in concern has some y value which is less than the y min. That is, it is in the bottom half space with respect to your clipping window. But for point P1, which has y1 as its y coordinate value, this condition doesn't hold. y1 is not less than y min. So the condition doesn't hold and b will be set to 0 or false. Now come to the t bit or top bit, rightmost bit. Just again go back to the condition. Fourth bit will be set to 1. That means t bit will be set to 1 if the point lies above or top of the window. That is, y is greater than y max. If y is greater than y max, y will be greater than y max while the point will lie above the top edge of the clipping window. That means on the above half space with respect to the top edge. But again, in case of point P1, this condition doesn't hold because y1 is less than y max. So just think for a while. What will be the value of t? I think you have been able to find it out. It is going to be false. So it will be 0. So if you think of it as a generalized condition, just have a closer look at point P1 once again. Point P1 is lying inside the clipping window and it has LRBT code 0000. From this we can conclude that for any point which lies inside the clipping window, it will have all the zeros as LRBT code. Just let me check with point P2. Will this condition hold, whatever we have been able to deduce here? Just write down the deducted condition here. For a point which lies inside clipping window, it will have 0000 as LRBT code. Now let me check the authenticity of this deduction with respect to point P2. Say the coordinate for point P2 is x2, y2. So what will be the L code for this point P2? It is left. Is it to the left of x min? No. So L is going to be 0. Is it to the right of clipping window? That is x2 greater than x max? No. Again, R is going to be 0. Is it at the bottom of the clipping window? No. Y2 is not less than Y min, so B code is 0. But if you look for the T code, now it is going to be 1. Why? Because Y2 is greater than Y max. It is at the top of the clipping window. So for a point which is outside your clipping window, this condition will not hold. In this way, you can perform the inside-outside test. Yes, inside-outside window codes can be generated by following the procedure which I have discussed until now. Next, our goal behind this algorithm is to clip the line. This can be achieved by using the LRBT codes for the endpoints of the line. So, how the algorithm goes? Just have a look at these statements. The logical OR of the endpoint codes determines if the line is completely inside the window. If you can recall, if both the endpoints of the line are inside the clipping window, the line will be trivially accepted. It implies that the line is totally inside your clipping window. Actually, here some mathematical way has been established to follow that trivial acceptance statement. The logical OR of the endpoints codes determine if the line is completely inside the window. If the logical OR is 0, the line can be trivially accepted. For example, if the endpoint codes are 0, 0, 0, 0 and 0, 0, 0, 0, the logical OR is 0, 0, 0, 0. The line can be trivially accepted. Okay, just now let me look into this trivial acceptance case. Say P2 and P3 is a line which is totally inside the clipping window. Now, how you can say that this line is totally inside the clipping window? Just by observation. Now, you have to establish this algorithmically by following this LRBT course. If you look at the endpoints of the line point P2 and P3 and try to establish the LRBT codes for the point P2 and P3, as both the points are lying inside the clipping window, LRBT codes will be all 0. Fine. Now you need an one point or one condition exit from the algorithm to establish the fact that the line is totally inside the clipping window. Just perform the logical OR. if you perform the logical OR of the LRBT codes for point P2 and P3, which are essentially inside, the result will be all zeros. So using this result, you can conclude that the line is totally inside the clipping window, and this can be trivially accepted. Just go back to the algorithm statement. It actually says the same thing. If the endpoint codes are all zeros, the logical OR will surely be all zeros. The line can be trivially accepted. That means you don't need any clipping, just accept it. However, just have a look at our previous line, that is line P1 and P2. Will the result of logical OR will be all zeros? No. If you perform the logical OR between the LRBT codes for point P1 and P2, it is going to be 0, 0, 0, 1. So you cannot trivially accept it, right? So in this case, again, two conditions or two situations might arise. What are the situations? You have to find out if the line is going to be trivially rejected. Just recall, before some time we have discussed that if the line is totally at the side of a edge of the clipping window, then it will be trivially rejected. But until this point of time, we don't have any condition by virtue of which we can say or we can establish that if the line will be trivially rejected or it is going to be partially accepted or clipped. Now we will try to establish that thing. So to establish or find the fact that is the line going to be trivially rejected, what you have to do? You have to do bitwise AND of the codes of LRBT. If both codes have a 1 in the same bit position, what will happen? The bitwise AND will not be 0. It will have 1 at some place of LRBT code. Then you can conclude that the line is outside the window. Then it can be trivially rejected. Now try to understand this concept in a simple way. What you have to do? You have to do bitwise AND of the LRBT codes. And the next step, two conditions might arise. The result of the bitwise AND condition might be all 0, and it implies that the line will be partially accepted. And if there are some ones, for example result is say 0001, it implies that trivially rejected. Now let me investigate this case. Uh, Now what you have to do? You have to perform bitwise AND for both the LRBT cores. Bitwise AND. Now if you look at the line P1 and P2, it is partially inside, and here you have the LRBT code for point P1 and here you have the LRBT code for point P2. If you do bitwise AND, you can find that all the bits will have zeros. So this first condition is satisfied. The line will be partially accepted. So you cannot go for this trivial rejection scenario. Next, just try to figure out what will happen if you do this bitwise AND operation for this line P4, P5 LRBT curves. You will find that at some position there will be a 1 in the result of bitwise AND operation. In that case, you will trivially reject this line. So this is your homework. You try to do this at home. Try to find out the LRBT course for point P4 and P5. Establish if the line will be trivially rejected or not. If yes, why? So this is your homework. So what was the essence of the discussion? If the bitwise AND operation of the LRBT course for both the endpoints of line are all zeros, the line can be partially accepted, and if at some location of the bitwise AND operation we have a non-zero value or 1 as value, then the line will be trivially rejected. Now again come back to the algorithm. If the line cannot be trivially accepted or rejected, then what happens? At least one of the two endpoints must lie outside the window and the line segment crosses a window edge, as it happened in case of our line P1, P2. One endpoint is outside the clipping window, due to which you cannot trivially reject it. In that case, it can be concluded that one point is outside your clipping window, and because of that there is some intersection with the line of some of the window edges is there. The line segment crosses a window edge. So what you have to do, you have to find that intersection point to clip the line. This line must be clipped at the window edge before being passed to the drawing routine. That means you have to find this intersection point, then you have to reject this portion of the line and accept only this portion. So this was the idea behind Cohen Sutherland line clipping algorithm. If you want to find out how to get the intersection points, here there is a method. This is not essential for your semester exam. This is only for your reference. And here there is an example in just whatever we have done here. This example is similar to that. Lastly, here are the references from where I have accumulated this material. So read the document carefully after watching the video. Hope you have learned something. Have a good day. Thank you.